Good afternoon, everyone. I am Sungmin Ho from Dankook University, South Korea. It is my great honor to give a keynote presentation at PAC Asia 2022. Today, I will talk about the analysis framework that we have recently developed to compare the sustainability of different chemical products by considering the global market dynamics. Carbon capture and utilization products are selected as an illustrative example to demonstrate the effectiveness of the developed framework. So recently, due to the environmental concerns, the concept of carbon neutrality is getting ever increasing attention, and we are given a lot of opportunities to design various sustainable processes such as CO2 utilization process, the production of sustainable polymers and biofuels and biochemicals, as well as various types of renewable energy systems. So in the design of these processes, it is very important to evaluate the performance of the designed processes by, for example, techno-economic analysis and life cycle assessment. So the key question that we would like to answer in this presentation is which product is the best when the same source is used? To answer this question, we have developed an analysis framework, and in this presentation, we're going to use the carbon capture and utilization network shown on this slide to illustrate the application of the developed framework. So in this network, we used the carbon dioxide as the feedstock to produce 6 different CCU products: gasoline, diesel, dimethyl ether, dimethyl carbonate, methanol, and succinic acid. And we have 13 different CCU processes in total to produce these 6 CCU products. Okay, so if we are comparing the same product produced from 2 different processes, it is okay for us to compare the unit reduction of these 2 processes to determine the relative competitiveness of between these 2 processes. So for example, if the unit reduction of carbon dioxide is given like this, shown on this slide for the product A produced from process 1 and 2, we can say that the process 1 is better than the process 2 because we can reduce more CO2 emission by producing product A from the process 1. However, if we are to compare 2 different products from two different processes, it is not enough to compare the unit reduction. Okay, so in this case, we also need to consider the global demand of 2 different products that we are comparing to determine which product is better to be produced in terms of carbon dioxide emission reduction. So for example, if the numbers are given like these, we can say that producing product B is better than producing product A, even though the unit reduction of product B is smaller than the unit reduction of product A. So if we multiply the unit reduction by the global demand, we can see that the total reduction in the carbon dioxide emission is larger for product B than product A. Another aspect that we need to consider in the evaluation of 2 different products is that the global demand changes with time. So for example, here I mentioned that it is better to produce product B from the viewpoint of CO2 emission reduction, but as time goes by, you can see from this graph that the global demand of product A is more quickly increasing than the global demand of product B. So right now, it seems that the product B is better to be produced than product A, but in the future, it will be better to produce product A than product B. So the temporal evolution of global demands of different products should be considered in the evaluation of different sustainable products. The final element that should be considered in the evaluation of different products is the market competition. So in a typical techno-economic analysis or life cycle assessment, it is assumed that the product produced from a sustainable process will simply replace the products produced from the existing reference process. But that would not be the case, always the case. So we need to consider different scenarios for the market competition. So two additional scenarios that we can think of is to balance the future demands by producing the products from a new sustainable process. And another scenario is the pure market competition between the existing plants and the new sustainable plants. So to develop a systematic analysis framework considering the global market dynamics and the market competition, we have adapted the concept of supply-demand model from the microeconomics. So here, the simplest form of the supply-demand model is shown as a graph. So here you can see two different curves. One is the supply curve, which has a positive slope. So it means that if the price of the product is increased, the supplier will produce more products. And the other curve is the demand curve, which has a negative slope. And this means that if the price of the product is increased, the consumer tends to buy a smaller amount of products. So the point where these two curves meet is the market equilibrium. So the price of the product and the quantity of the product traded is determined by the position of this point. So if the global demand of the product is increased, the demand curve will be moved to the right, as shown on the graph on the right hand side. And in this case, we can see that the amount of the product traded is increased, and price of the product is also increased. And in this case, the supplier can increase the amount of the product produced, as shown on in this graph. And in this case, by increasing the supply rate of the product, the market price is brought back to the original price. However, the amount of the product traded is increased more, so the supplier can obtain more profit by producing more products. On the other hand, if the supplier decides to increase the supply rate of the product while the global demand of the product remains constant, the amount of the product traded can be increased, but the market price at the same time is also decreased. So the overall profit of the supplier can be lowered by increasing the supply rate. As I mentioned earlier, the demand curve and the supply curve shown in this graph are of the simplest form, which is linear lines. So these lines can be written as mathematical equations like these. So here what we know is that the slope of the supply curve has a positive slope, and the equation for the demand curve has a negative slope. So by using these two equations, we can obtain the explicit expressions for the market equilibrium conditions. So QE is the amount of the product traded in the market, and PE represents the market price of the product. So we have made two modifications to the supply-demand model shown on the previous slide. So the first modification was to explicitly consider the effects of raw material costs. And the other modification is to transform the supply dynamic model into a dynamic supply-demand model as shown here. So here you can see that the quantity or the price is now a function of N, which represents the calendar year. With these modifications, we can obtain the new market equilibrium conditions. So the final equation is shown here, and in this equation we can see the appearance of a new term, which is QSAD. So we have QSA and QSAD. So QSA is the amount of product produced from the existing plant, and QSAD in this case is the amount of product produced from the CCU plant. So this equation basically describes the changes in the market price due to the excess supply of the product from the CCU plant. So in this model, we have some parameters, for example, AS and AD, which are the slope parameters, and some more parameters like B1, B2, or B3. So to determine the optimal values of these parameters, we need to solve some parameter estimation problems using the historical data of, for example, the raw material cost and supply and demand of the product and the market price of the product. So once we identify all the optimal values of the parameters, we can use the dynamic supply-demand model to predict the future market equilibriums. So to predict the future demand of the product, we used the concept of compound annual growth rate, which can be expressed as mathematical equations like this. So here we can see that the results of the parameter estimation and the performance of the dynamic supply-demand model that we have developed. So A is gasoline and B is methanol. So from these two figures, we can see that the supply-demand model that we used can predict the market price of these two different products quite accurately. So now with this dynamic supply-demand model, we can develop an optimization problem which can be solved to determine the best CCU product among 13 different CCU products. So this optimization problem is basically a nonlinear programming problem, and in this problem we have different types of constraints. So we have mass and energy balance constraints, and one of the most important constraints in this optimization problem is the non-negativity of CO2 reduction. And also we have implemented some constraints representing the market competition, and also we have the dynamic supply-demand model that we have developed as a constraint in this optimization problem. While solving this optimization problem, we considered two different objective functions. One is the gross operating margin, and the other is the CO2 reduction potential. So these two metrics are used to evaluate the economics and the sustainability of the overall CCU industry, and to evaluate the economics and the sustainability of different CCU products, we defined two additional metrics shown here. So these metrics can be obtained from the industry level metrics using these equations, and we can see that these metrics have slightly different units. So these two scatter plots show us the relative competitiveness of 13 different CCU products considered in this study when the global market dynamics are not considered. So using the results shown in the scatter plots, we can summarize the rankings of different CCU products in terms of the economics as well as the sustainability. So by looking at these bar charts, we can make some conclusions about the optimal product portfolio for the CCU industry. So the first conclusion that we can make is that it is best to produce DME6 and SA13. So SA13 is mainly produced to increase the economics of the CCU industry. However, this product has a negative CO2 reduction potential. So to compensate this, we also need to produce the second best product in terms of the economics, which is DME6. Here we can see that this product has very good CO2 reduction potential. So another conclusion that we can make is DME7 and DME8 will not be included in the optimal solution in any case, because DME7 and DME8, they both have smaller values of GOMC and CO2RC compared to DME6. And the last conclusion that we can make is DME12 will not be included in any optimal solution because it is worse than DMC11. So these conclusions are true if we do not consider the global market dynamics. However, I will show you that these are not true if we consider the global market dynamics. To illustrate the effectiveness of the analysis framework that we have proposed, we considered 4 different scenarios. So the first scenario is to replace the existing plants with CCU plants, and the second scenario is to balance the future demands by producing the products only from the CCU plants. And the third scenario is the pure competition between the existing plants and the CCU plants. And the final scenario, which is scenario 4, here we consider larger CO2 source compared to scenario 3. So in this scenario, all the other conditions are the same as scenario 3. We just have 10 times larger CO2 source. So here what I am showing you is the single objective optimization results for the calendar year of 2025. So from this figure, so in this figure, G means that the solutions are obtained by maximizing the gross operating margin, and C means that the solutions are obtained by maximizing the CO2 reduction potential. And here the S represents the scenario. So S1 is the scenario 1, S2 is the scenario 2, and so on. So here we can see that for different scenarios, we have quite different optimal product portfolio, and if we are to replace the existing plants with the CCU plants, DME will be the best CCU product to be produced in the calendar year of 2025. But we can see that in the case of pure market competition, which is the scenario 3, methanol will become a better product than the dimethyl ether. Also, as we increase the scale of the CCU industry, so as we go from the scenario 3 to scenario 4, we increase the scale of the CCU industry by tenfold. And we can see that methanol is even more important in terms of the CO2 reduction potential. And in the case of gross operating margin maximization, gasoline is also selected as a part of the optimal solution. So here we can see that as we consider different market competition scenarios, the optimal product portfolio changes quite a lot. We have also solved some multi-objective optimization problems, and here what we can see is that the scenario 1 is quite optimistic. So in this case, even if we maximize the CO2 reduction potential, the CCU industry remains economically positive. But as we go from the scenario 1 to scenario 2 to scenario 3, we can see that the economics and the sustainability of the CCU industry becomes worse and worse. And if we increase the scale of the CCU industry, if we consider the market dynamics and the market competition, we can conclude that the CCU industry can never become economically positive. So this conclusion cannot be obtained from the traditional analysis framework. So here I am showing you the optimal solutions that we have obtained by solving the single objective optimization problems for different calendar years. So here the major trend that we can observe is that dimethyl ether becomes better and better as time goes by. This trend can be explained by the growth in the global market demands. So from this figure, we can see that the global market demand of DME is much smaller than that of methanol in 2020 and in the near future. But here we can see that the global market demand of DME is expected to be larger than that of methanol in approximately 2050. So the growth rate of the global market for DME is faster than that of methanol. So now let's look at more detailed results of the optimal solutions. Here we can see that DME7 and TMC12 are also included in some optimal solutions. So I mentioned that if we do not consider the global market dynamics and the market competition, these two products will never be produced. But here, as we consider the global market dynamics, the optimization problem determines that these products are also worth production. So to see why this is the case, we can look at the changes in the performance metrics of different CCU products. And so basically here, if we produce more products from the CCU plants in the presence of market competition, we're going to flood the global markets. And if we flood the global markets, the products that we produce will become less valuable. So these changes in the performance metrics can be quantitatively captured by the dynamic supply-demand model that we have developed, and example is shown on this slide. So in the calendar year of 2025, we can see that if we do not consider the global market dynamics, DMC11 has a higher value of CO2RC, which is sustainability metric, than DMC12. And also we can see that DME6 is better than DME7 in terms of CO2RC. But as we produce more DME and more DMC, we can see that the relative competitiveness between DMC11 and DMC12, or between DMC6 and DMC7, changes. So the value of CO2RC decreases more quickly for DMC11 and DMC6 than DMC12 and DMC7 respectively. However, as the global market demands grow as time goes by, the enlarged global market acts as a buffer. So in the calendar year of 2050, we can see that even though we produce more and more DME, we can see that the value of CO2RC does not change that much for DME6 and DME7. So in this case, DME6 is always better than DME7, regardless of the amount of DME produced. So in this case, so in the calendar year of 2050, we do not produce any DME7 or DMC12 as we did in the calendar year of 2025. We were also able to estimate the maximum capacity of CCU industry, and by doing so, we observed that the maximum capacity of CCU industry can be overestimated if we do not consider the global market dynamics. Finally, we can also evaluate the effects of government subsidy using the analysis framework that we have developed. So here we can see that as we increase the government subsidy in the calendar year of 2050, we can increase the maximum capacity of CCU industry by producing more fuels. To conclude, we have developed a novel process analysis framework by considering the global market dynamics. So here we have adapted the linear supply-demand model from the area of microeconomics, and we have modified this simple supply-demand model so that we can consider the price change in the global market by the excessive supply from sustainable processes. So in this case, the CCU processes. And by solving the optimization problems for various cases and scenarios, we observed that the sustainability of carbon capture and utilization highly depends on the market conditions. And we identified that the best products for the short term and the long term are methanol and dimethyl ether respectively. So one of our future research directions is to apply the analysis framework that we have developed to different industries. For example, some types of biorefineries. So thank you for your attention, and I will be happy to answer any question that you may have.